Hello student, I'm going to start from the last topic that has been discussed in the previous video, that is about B-spline. We are discussing this curve representations in computer graphics system uh, in this last two videos. Now this is the last video in this line, so that is about B-spline. So it's basically a generalization from Bezier curve, and in case of Bezier curve there is also local control points are there through which we can control the curve. Here also same local control points are there to control the curve, but degree of resulting curve is independent to the number of control points, and also it has better control over the curve, but the degree of the polynomial or the degree of the resulting curve is independent to the number of control points. Next is math representations like the Bezier curve. Here is also we can see a mathematical representation. Here one equation with k minus 1 degree of polynomial with n plus 1 control points. Here you can see I equal to 0 to n, and that is why we can say n plus 1 control points, and every control point will associate the value of u. U is the parametric variable. So here you can see it may be start from p0, p1 to pn, that is n plus 1 control points, and in that way it will go on. And ik that is B-spline function to be calculated in a recursive form. So we need to calculate that part, that is the B-spline function, to find the actual points of the curve. So this is the equation to find the value or to find the value of the B-spline function. So here this is the equation. So here this is also associated with the parametric variable u. So now we can see what is parametric knots in case of B-spline curve. Here u, z, that is parametric variable, or we can say parametric knots or knot values for an open curve B-spline. And the uj, here you can see uj or any variable ui can be, the value can be lies in these three values: 0 or j minus k plus 1, n minus k plus 2. So what is the value of n? N is the control points. Okay, j minus 0, uj will be 0 if j less than k. So where we can see here 0 less than equal to j less than equal to n plus k. Thus if a curve with k minus 1 degree, suppose the curve has k minus 1 degree and n plus 1 control points. So degree is suppose k minus 1, and the control point is to be developed is n plus k plus 1. So we need to develop n plus k plus 1 knots, or you can say control points. They then are required with 0 less than equal to u less than equal to u max n minus k plus 2, n minus k plus 2. If j greater than n, then n minus k plus 2. If j is between k less than equal to j or j less than equal to n, then j minus k plus 1 or 0 when j less than k. We will understand if we go to an example. So the curve is expressed by this equation as like this. where ni is this equation. This equation is the recursive expression. This equation is a recursive equation, and the base case ni1 is defined as is the recursive equation nik. Nik is the recursive equation depends on n j k minus 1, where j is a generic I. So here you can see nik depends upon nj k minus 1. So that is, here you can see, and the base case ni1 initial value is defined as initial ni1 value is ni1 will be 1 for mu I less than or equal to mu I plus 1, 0 otherwise. If it is not satisfied, then it will be 0, and the knots ui are found based on the following. So this is the equation to find the parametric knots. So we need to evaluate the B-spline curve. Define k and n. We need to define the k and n, where k minus 1 is the polynomial order and n plus 1 is the number of control points. So such a way that we need to define the k and n, value of k and n, so that k minus 1 becomes the polynomial of the curve and n plus 1 becomes the number of control points like this one, p naught dot pn. Then we need to find the knots using these things. We need to find the knots following the conditions. This is done by applying rule 4 for each of ui. So using these rules, we need to find out the knots. Find ni1. We need to find ni1 using the base case rule. This is the base case rule. We need to find this ni1 using that rule. It might be 0, n01, n11 dot n minus 1 like that, and I will be from 0 to n. That is why I is from 0 to n minus 1. Fine. Note that you have to apply the rule that 0 by 0 equal to 0. So here actually in computer or in if else condition, if we put 0 by 0 is infinity, then it will not work. We need to put 0 by 0 equal to 0. That is why it is saying ni2 equal to n02 and 12 like that if it is 2, if it is 1, and b ni3 like that. If you keep k equal to 3, k means that value k, that whatever you define, and it is linked with the polynomial order of the curve. Keep repeating until you reach the defined order k, until you reach the defined order of k. In that way, you need to find out the values of n. With the last step in 4, the nik this have been obtained, and simulation in 1 can be performed. Simulation in 1 can be performed. Obviously, in order to compute the curve expression, the coordinates of the points pi needs to be known too. So in that way, we will try to go through the equation and through an example, then we can understand. Here you can see nik, this is the equation given for the knot value calculation. Nik f of nik minus 1 and ni plus 1 k minus 1. So if we start from k plus 1, k equal to 1 means the base n, where n equal to 3, so 4 control points. That is why k equal to here you can see n plus 1 are the control points. So if n equal to 3, then 4 control points. And also if n increases, wider the base. This base will be wider when n is increases. K equal to 4, then 4 minus 1 equal to 3 cubic polynomial. Our equation or our equation of the curve will be cubic, polynomial will be cubic. And again we have to follow this one, 0 less than j and plus k equal to 7. So n equal to 3, k equal to 4, that is why j will be vary from 0 to 7. So now we have to go through like this, we have to find the n values. So it will be 0 to this way, 0 nik, 0 k to n minus k k. So here 0 1 1 1 2 1 3 1 4 1 5 1 6 1, because I will be less than equal to 6. Then for k2 we need to find the n02, n02, n12, n22, n32, n42, n52. That is I less than 5. When k2 increases, this I is decreases. In that way, this is k equal to 3, n03, n13, n23, n33, n43. So for each value of k and I, we try to stack them up, and the value are associated with the value of n and k. So number of control points independent of degree of polynomial. In case of B-spline, property was that number of control point independent of degree of polynomial. So suppose this is this initial line, initial curve is quadratic B-spline, but this one is a cubic B-spline, but this one is a fourth order B-spline. Okay, when k equal to 5 or when k equal to 4 or when k equal to 3. The higher the order of the B-spline, the less the influence the closed control point. So when the order is higher, then these close points, the controlling points has less effect on the curve, has less effect on the curve. That is what it is saying, that is why it is saying that the control points might be independent with the degree of polynomial, and when it is become only linear, then k equal to 2. But when 3 it becomes like this, when 4 it becomes like this, when 5 it becomes like this. So the higher the order of the B-spline, the less the influence to the closed control points. Here you can see n equal to 3. So n equal to 3 means number of sections is 3, number of section is 3, but control points are 4 control points are there. B-spline allows better local control. Shape of the curve can be adjusted by moving the control points. Here you can see 1 2 3 4 5, origin value is 5, then 6 7. So by moving the point 5 to here, this whole curve can be changed. So you can see this is yellow for the original position, but the blue position is due to the changing position of 5, and the green position due to changing position of 5 to here. So by changing the, or by moving the control points, we can change the shape of the curve. That is why B-spline is better, or B-spline allows better control, better local control. Local control is actually a control point only influences k segments. So local control means this control point can only control some part of the segment of the curve. So here you can see, due to the changing position of 5, this part only got changed, but remain part of the curve almost stays like previous, orientation. So when 5, the position of the 5 control point is changed, then the also that part of the curve also got changed like this and like this due to the change of the control points, and that is why you can say that is local control, and local control is better in case of B-spline. Repeated values of control point can pull a B-spline curve forward to vertex. So we can say that is interactive curve control. So here you can see P0, P1, P2, P3, P4, P5, P6, P7 and K equal to 3. So add more repeated control points to pull the curve. 1 point at P3, 2 points at P3, 3 points at P3. So repeated values of a control point, suppose P3, if we use repeated values of a control point, can pull a B-spline curve forward to vertex. So if we repeatedly pull this curve by using more points, of the curve, by controlling from this P3, this whole spline curve goes forward to the controlling vertex. So here actually that is why this is interactive curve control, means we can interact with the curve from the controlling point, but the order of the curve polynomial remain same. So we can add more repeated control points to pull the curve. Find the equation. Suppose we can go for an equation of cubic B-spline curve defined by a same control point as in the last example. How does the curve compare to the Bezier curve? We'll go through an example right now. The coordinates are given like this, as like the Bezier curve: P0, P1, P2, P3, P0, P1, P2, P3. Find the equation of the resulting Bezier curve that we have done in the Bezier curve example. Also find points on the curve for 0, that is u value are like this. So using those equations in the Bezier curve, we can find this Bezier curve and we can generate the points here. This is u for 0, u by 1 by 4, u equal to 1 by half, u equal to 3 by 4, u equal to 1. So that has been discussed in the last video. But in case of B-spline, we'll see how it goes. So find the equation of the cubic B-spline curve defined by same control point as in the example 5.19, as in this same like this one. So cubic curve, then we if it is cubic curve, then polynomial is 3, then k equal to 4, because that is the k plus 1. No, degree plus 1 is equal to k. So we need to put 4 points and n equal to 3. 4 points, then there will be obviously 3 segments: 0, 1, 2, 3. And our equation of ui, u naughts or parametric knots: 0, j minus k plus 1, n minus k plus 2, and 0, k is what? 4 and plus 1. So minus 4 plus 1 minus 3, and 4 plus 2. So n is what? N is here 3. 3 minus 4 plus 2, that is why 1, 0, 1, or j minus 3. So that is j less than k equal to 4, and 4 less than equal to j less than equal to 3, or j greater than 3. And u varies from 0 to 1. And maximum u is n minus k plus 2, that is 1, because n minus k is 3 minus 4 plus 2, that is 1. That is why u maximum value is 1. So 0 minus less than equal to j less than equal to n plus k equal to 7. So n plus k equal to 7, 3 plus 4. So this is the original equation for the B-spline curve, where we need to find the functions n, I, k. So thus this cubic spline has k equal to 4 and equal to 3. So we need to find 8 knots are needed to calculate B-spline curve. 8 knots, why? Because there will be initially there will be 4 n knots, then in the upper there will be 3 knots, then there will be 1 knot. So that is why 8 knots, like you have discussed here. Okay, like this one, there will be 8 knots. The way we have find this NI value, not calculation. So here we can see in this example also we will find 8 knots need to be calculated for the B-spline functions. So U0, U1, U2, U3, U4, U5, U6, U7, these are the knots. So that is what this is. Use A, that U is not 0 less than equal to J less than equal to 7, that is why 0 to 7, that is why 8 knots, 0 to 7. The range of U, 0 less than equal to U less than equal to 1. Value of U is between 0 to 1, but not number of knots are 8. PU is this one, this equation. PU is this equation because we got that from here. Here from this equation we can get that from equation, and this is the equation for knot calculation. And again k varies from 1 to 3, 4. That is why this also n equal to 3, 4 control points, and k equal to 4, 4 minus 1, 3 cubic polynomial. We need cubic polynomial, that has been given in the question, cubic curve. So that is why this follows like this. For this function ni k, that is the function for the B-spline curve. So cubic curve k equal to 4 points, n equal to 3, 0, 1 to 3. Calculating the knots, use A. So we'll go from 0 to 7. So here you can see 4 zeros and 4 ones. Why? U0 here you can see if J is less than equal to 4, then we can directly put zeros, but if it is greater than 3, then we can directly put the ones. If J is greater than 3, then I can directly put the ones. If it is less than 4, then we can directly put the zeros. That is the thing we can get, that is the knot points. Okay, now we need to find the NIK. So NIK can be found in this equation. So NIK is this, for k equal to 1, using the knots and using these things that has been discussed. Here also you can see I equal to 0, 1, 2. I equal to 0, 1 and 2. So I equal to 0, 1, 2, ui equal to 0, less than equal to u, less than equal to ui plus 1, that is also 0, ui plus 1 equal to 0, or u equal to 0. So like this, using this equation, so n01, n11, n21 equal to 1 or 0 in case this is at u equal to 0, otherwise this one will be 0. For i3, u equal to 0, less than equal to u, less than equal to I plus 1, that is 1 here, or 0 u less than equal to 1. So that is why in this case also it might be 1 or 0. it will be 0 because that is lies between 0 less than equal to u less than equal to 1. In the, here also it is 1, n0 1, n1 1, n3 1, that will be also 0 1 because u equal to 0, because that is why 0, because that follows this equation. Okay, and this also 1, and again and 4 1 5 1 6 1, that also, because that also follows this equation, then also it will become 1. This follows this equation, e equal to 1. Same way this is for k equal to 0. Okay, next k equal to 1 2 3 4. In that way the things will go on to find the value. So substituting the ni4 into the equation 5115, so using in this equation okay, so we'll get this equation. This equation is the same as the one of for the Bezier curve in the example 5.19. Thus the cubic B-spline curve defined by 4 control points is identical to the cubic Bezier curve defined by the same points. This fact can be generalized for a k-1 degree curve as mentioned earlier. So n plus 1 control points, 3 plus 1 equal to 4, and degree of the curve is 4 minus 1 3. So 4 control points and cubic polynomial, which is same as like Bezier curve. So that is how, and these things will go on using the recursive process. That is why we need to go for more calculation, but don't need to go for more working on this one. Just understand how it flows, how process flows, that is more important, and try to understand basic things behind the Bezier curve and B-spline curve, how they are related and why they are different, and what point and what are the control points, what are the degree of the curve, and how they related. If it is using if we use the equation, how they are same. Those are important point to be noted. There is also one more topic here in this slide, that is non-uniform rational B-spline curves, but I will not go through it. But if you have if you want to go through that topic, you can go through it. I have already uploaded these slides in Google Classrooms. This whole topic about the curve representation is a bit tough, so no need to go through more about the mathematical explanations. Try to understand the main idea behind or main properties of the curves, and main way to how we can display the curves using what type of concept. Those theoretical ideas only will come in the exam. So try to give just a just a brief reading on these things. You can get more ideas in the book also, and if you find any difficulties or any issues, let me know. And also if you want to add something more in this, you can also let me know. We'll talk over Google Meet. Okay, so that's it all about curve representations. Next point onwards, we'll try to go for module 4. This module a bit in last part of this module, that is about curve representation, is a bit tough, so I just advise you to go through the book at least once for more understanding, and then only you can know your drawbacks in this scenario. And if you have anything to talk or anything to share, let me know. Thank you.